Hello, my name is Bakri Dasuki, physics teacher. I'm gonna be your teacher for the lesson of today. For the students who are in level IGCSE 2, today we're gonna take Unit 8, Electricity. As you can see, we finished 8.1, 2, 3. Now we're gonna today start with 4. As you can see here in the book, page 171. 1.8 electricity. So today we're gonna start with page 178, as you can see, okay, with current in simple circuit. So let's talk what is the current in simple circuits. For example, here we have a battery or a cell that gives us electrons, okay? So the electrons, because of the chemical interaction between the cell, so as a battery, for example, it gives us electrons. So the electrons is flow including the connecting wire, okay? For example, in this circuit. So the thing here is we have a switch, but it's now still connecting. Nothing happens. So electrons are going down. Okay, connecting, depending from the connecting wire from the negative pole to the positive. But here we have a lamp and we have a filament, very thin filament wire. Probably it's made from tungsten. So when it's coming there in, what happened to the lamp? It's glowing. Okay, and the electrons will continue to the cell and they keep doing that. So now question, why is the lamp is glowing? Okay, the lamp is glowing because there's a huge amount of electrons are flow inside the filament that make it glow, and that make the lamp turn on. So how am I gonna turn it off? Even if I move the cell so there is no electrons, here we have a switch. So the switch is it's even two sides, even on or off. Okay? So if it's on, it's connecting for connecting wire. But if it's off, here it's cut the connecting wire. If you look close to the switch, will be like this. So, or the symbol for the switch, so it won't be connecting. So the thing is, what will happen? The lamp will be turned off. Why? Because the switch is open. So we don't have any circuit without it. It's all connected from the negative to the positive pole. So the thing is, for the switch, it has also, like we say, should be really connected. So it give us the glowing for the lamp. Okay? As this example, every one of your room have a lamp. As you can see, here is the lamp. So this is the switch. As I'm holding this is switch. Okay? And here is the lamp. So the lamp now have a generator we have electricity from the generator until here. So in this case, the generator is the cell that gives the electrons. So the electrons coming for this switch and this connecting, this is the switch, and the lamp here is this lamp. So what should it mean? When I cut the switch, it's turned off. When I switch it on, it's turned on. Okay? So you already use this example in each day, literally in your daily life. So also there's circuit symbols, as you can see here. This symbol is for the cell. Okay? This for connecting wire can be copper. Usually most of the time it's copper or aluminium. Here is the switch. Here is the lamp. And here is the ammeter. So how we can draw this in the symbols? We can put the cell, then the switch, then the lamp, then you build with the connecting wires. So you have to be always notice that the long one is what is the positive pole, like you can see here, and the short one is the negative, where the electrons is moving. Okay, clear? Now we move along with something measuring current. Now this current, as you see, it's what? It's flowing here, right? So how I can measure this current? So the current is what? It's a flow of high charge, and it's about 6 million electron per second. So that's actually a lot of amount. So the measuring current is in ampere, and the scientist, the French scientist André Ampere, who find this out. So we don't use this amount usually for the small calculation. So it's divided to 1000, so milliampere. So each 1 ampere is 1000 milliampere. Okay? So more current we have, more ampere, that means what? More flow of charge. Okay? So more flow of charge, that means more current, as you can see here. So you get back to ampere for this circuit. So how I can measure that? Thing is, there's an ammeter. We're gonna put it here after the load, and it's gonna give us what? The load. So this ammeter affect the circuit? No, it's almost not affected. So don't take that much thing to measure. So it's almost don't change the result that take it for the lamp. Okay? So this like some typical current values for the touch lamp is 0.8 ampere. That means it's what? Including to this, it's 0.2. That means 200 milliampere, or 0.8 with 0.2 ampere. And the charge light, the car headlight lamp, it's 4 ampere, and the electric kettle is 10 ampere, as you can see here. So we're talking about the charge. The charge is in what? It's column. Okay? So the charge is the current in time. So every second, with 1 ampere that it passes 6 million electron, it's 1 coulomb. Okay? So for example, of course the current is ampere, the charge is coulomb as we see, and the time for sure is second. So a simple example, if we have 3 ampere, okay, current, it's passed by for 2 seconds. How much is the charge? As we hear with the law, charge is current in time. So charge is 3 ampere in 2 seconds. Charge is 6 coulomb. Okay? And go on. Now we go to the current direction. So conventionally they say that current is going from the positive to the negative. But actually, the real thing is the electrons are moving from the negative to the positive. That's why it's the electron direction. Okay? But now we want gonna try to measure if we have something, if we have 2 emitters, and here is in the same mode. Does each emitter give us different reading? Actually no, it don't. Each emitter, if they are in the same circuit and they are one load, they give us one read. So this ammeter, for example, is 2 ampere, and this will be 2 ampere, including to this circuit. Okay? So moving along to page 188.5 or 8.05, and we're gonna talk about potential difference. So we're going to continue with 8.05, the potential difference. It's on page 180, as you can see here in your book. So first of all, we're going to talk about potential difference or voltage. What does that mean? So as we take the last example for the cell, if you have here a cell, so the cell, we said that it gives power, right? So the power, or the electrons, it's the power, are coming out from the cell and going to the lamp, including this thin filament, and it keeps going to the positive part from the cell. So that when the electrons coming to this lamp, it will glow. Okay? When it's glowing, that means what? There is a power in it. So what happened to the cell actually when the lamp is turned on? That there will be current. So for example, this cell is 1.05 volt. What happens when the electrons start here, the potential power the electrons will be wasted here. Okay? So the volt will be less than 1.05 volt here. Okay? So the thing is, more current, that means less voltage or less potential difference. As you can see, the scientific name for the voltage is the potential difference. So what does that mean? That means in every 1 volt we have, it's 1 joule per coulomb. Per coulomb, that's for charge, we talked about that already. So more current here, that means less volt. Why? As you see here, the power is wasted with the electrons. For example, a car, you know the car battery, it's about 60 ampere normal cars and 12 volt. Let's focus on the volt. So the car usually is 12 volt, okay? So if it's 12 volt, but when the car is not moving. So when we turn on the car and we start the car, the volt will go down to 9 volt, from the 12 to 9. Why is that? As you say, when there will be more current, that means the volt will go down. Why? Again, because the wasted electrons on the load. Okay? Now we move apart to cells in series. So how we gonna do if I have just a cell? It's 1.05 volt, but I need 12 volt, for example, or 6 volt even. So it is actually the battery. It means it's a joint of connected cells. Okay, so every cell is 1.05 volt. That means in conclusion, the battery is 6 volt. Okay, so more cells, that means more volt in the battery. Let's see, 1.05, 4 times it's 6. Of course, for the symbol, you found it like this. That means this one cell and this other cell, and here is the cells between. Continue, we will here around the circuit. So we take ammeter for measuring the current. But now how I'm gonna measure the volt? But the directional difference here around the circuit, for example, we have here two cells, let's say 1.5 volt. If I bring a voltmeter and put it here, it will give me 3 volt. Okay, let's focus here. Now, let me bring another color to know the difference. So, if I have here small lamp, and I have here big lamp, I have here the source or the cells or the battery, whatever, it's 3 volt. Okay? So the thing is, the current coming up from here, taking up the filament, what we say here, the volt will go down. Continue, again the volt will go down, coming back to the battery or to the cell. So we find here that if we take a volt ammeter, first of all, a volt ammeter, it's not connected like the ammeter. The volt measurement, it's not connected as the ammeter. So if we have here a normal cell, okay, with the lamp, as we say, or let me put the normal symbol for the lamp, I can put here ammeter and connect it. And I know the current for the circuit. But then the voltage, no, it's not like this. For the voltage, it is, let's draw another one. I have here lamp, and here the source. I have to put the two sides for the voltmeter. I have to put them on the sides of the load. And if I want to know the cell, I have to put them in the sides here. Here should be the voltmeter, and here should be the voltmeter. Okay, so we know the directional difference. Of course, as the ammeter, it don't take energy, so it's like connecting wire. So here, how I'm gonna know that? We put here a voltmeter. So it's gonna give me 3 volt. Why? Because it's two cells, 1.5, or a battery, or whatever. So now what's happened? Let's focus here. A small lamp, it takes 1 volt. What? Joule per coulomb. That's mean it takes power from the charge. That's mean here, if I bring a voltmeter here, it'll give me the reading of 1 volt. Okay? Not 3, 1. Because this is the what? The power wasted, because there is more current. But here the big lamp will give me a reading of, here is 2 volt. So it'll give me a reading for 2 volt. Why? Because it's bigger lamp, that's more power wasted. Okay? So in conclusion, 1 volt and 2 volt will give us the 3 volt, like as much as the battery. So almost there's no power extra, just like the connecting wire take nothing, like you can finish it. So for this, let me say 1 volt, 2 volt. Why? Because this is smaller and this is bigger. Small lamp and big lamp. So how are we gonna draw this in symbols? As we can see here, here's the cell. Here the 3 volt. Here's the first small lamp, and this is the big lamp. So this, if we put the voltage meter here, it will be 1 volt, and if we put voltage meter here, it will be . So we're gonna continue with 8.06 resistance. First of all, today we're gonna talk about resistance. As you can see in your book, page 182. Okay? So, what is resistance? For example, I have normal circuit, I have the cell, then I have the lamp, and it's going back with the connecting wires to the battery. So we say the connecting wires, they have what? Resistance. But it's low if the connecting wire is copper. Now what if the connecting wire is from nichrome? Actually what will happen that you need much more power to torch up this lamp. Why? The thing is because the nichrome, it have much more resistance than copper. What does that mean? That means I need more power. So when I use connecting wires like copper that have low resistance, I need less voltage than the nichrome, because the nichrome have more resistance. So how I can calculate the resistance? The resistance is given by ohm, okay? It's given by ohm, and it's the Greek letter for omega, and it's the potential difference, the voltage, on the current in ampere. So for example, I have a cell or circuit with 6 volts and that have current 3 ampere. What is the resistance for this circuit or for this connecting wire? So as we say, it's volt on ampere. So the volt is what? Volt on ampere. The volt is 6, that's a coil. Volt is 6 on 3. That means I have resistance on 2 ohm. Okay? How I can find the resistance, how I can find the current, how I can find the voltage, simple, use this parameter. If you want the voltage, just cover it and you have to multiply I on R, the current resistance. If I want the resistance just like now, I cover it, I divide voltage on the current. If I want the current, I divide the voltage on the resistance. Okay? So this you can use this way for 3 equations from this. Okay? So some factors affecting the resistance. What affect my resistance? First of all, the length. Like if you double the length, it's double the resistance. If I have 1 meter of connecting wire, for example, as a cover, if it's double length, that means it's what? It's double resistance. Okay? Second of all, cross-sectional area. So when I have halving the end of a normal wire, so when it's the half of the end area, it takes actually more resistance. So the thinner the wire is, the more resistance it is. Okay? Let me also here, material, like we say, if it's nichrome wire, what? It's more resistant than copper. So it's very important what is the connecting wire is made of. Okay? Temperature. For metal conductors, when the resistance is bigger, when they have more temperature, the resistance is what? Is higher. But for the semiconductors, when I have more temperature, the resistance is going low. You can see the figure in page 182. You can see here the resistance go from down to up. Short, thick copper wire, long, thick copper wire. That means the long, thick copper wire is more resistance than the short, thick copper wire. The thin, long copper wire, it's more resistant from the first and the second. And long, thin nichrome wire, that means it's more resistant from all these 3. Continue with the effects. To say the heating effect. How we can use this resistance as a heating? So the heating effect, the electrons lose energy and the atoms gain it. So when there's resistance, the electron, what happened to it? It actually loses energy, and this energy goes to the atoms and make it more vibrate. That means more temperature. Okay. So actually, this is why how we heat. This is how we use the hair dryer. This is why how we use the toaster or the warmer or any heat or the oven, etc. So usually they are making this filament or this wire are made, or it's made from nichrome. Why nichrome? It have what we like to say very high resistance. That means more electrons are losing power, more vibrating for the atoms. That means they're gaining more weight. And the small torch lamp usually is made from tungsten. Why? Because it have high. It usually you see it's so thin. That means more resistance, as you see inside the lamp, and it have what high melting point. So the metal won't melt easily. Okay. Like we said, this here examples like the hair dryer, the toaster, the oven, etc. The electrical one, of course. Move along for resistance components. First of all, we keep the volt and the ampere. What we use this resistance. So the main use is for keeping the voltage and the current for certain components in complicated circuits, like for example TVs, radios, computers. So you will see it's full of resistance. Why? So they can manage that not more voltage or not more current coming to this component. Okay? So the resistance have very different value. It starts like from 1 ohm until 1000 ohm, and it's 1 kilo ohm, like you see here. 1 kilo ohm, that means 1000 ohm. And 1 mega ohm, that means 1 million ohm. Okay? Until we have many mega ohms, like many millions of ohms. Then we go to variable resistor. Sorry. Let me draw this for you so we understand how this variable resistor is working. That's enough. So, for example, we have here cell. I have here lightweight lamp. Now, imagine you have a long bar, and around this bar there is what? There's a wire that is connecting. Okay? Or let me listen. Okay. So here is the stand here that define where you are. If you are here at the beginning, okay? So what is the variable resistance? What is the goal of it? It's give us more than one value for one resistance. So it's change the value for this resistance. So when we move this, for example, till here, what will happen? What will happen is what? The length of the wire is what? It will get longer. And as we say here, more, or the fixed one here, more length, that's mean what? More resistance, exactly. So more I push it, that means the wire is, the length is getting more. Okay? So more length, what does that mean? That means more resistance. So we change this up and down, less resistance and more resistance. What will happen with us? It's playing with volt. So when I play with ohm, what will change? It will change the volt. Like we see, if we want the volt, it's the current multiplied the resistance. So if I will change it, what will happen to this lamp? It will go, the light will go even more brighter, or it will go what? Just a small light. Light is going up and down, like your brightness in your mobile phone. It's true that you put your brightness going down, it is giving an electric signal that's turned for the resistor, the variable resistor, that change up and down, the power is going to the screen, to light your screen. Then we go to the thermistors. Thermistors are giving a high resistance when they are cold, but they're giving a much lower resistance when they are warm. Okay? And there is a light dependent resistors, and they call them LDR. And this is very interesting resistor because in the dark it have very high resistance, and when it gets light it have much lower resistance. So when they use it, usually they use it in automatically light in the parks or in the streets. So when it's daylight, the street light will turn off, okay? Or in the parks or wherever. Or when it's dark, what will happen? The LDR will make the current pass and will turn off the light, okay? So it's automatic procedure, so you don't need to turn off and turn on each day for the whole park or for the whole streets you live in. We're moving to the diodes. The diodes, they depend on the direction of the current. So in one direction they have very, very high resistance, and the other direction they have very low resistance. And usually they used in electronic circuits most of all. How we can see, you can see the examples. So let me draw it for you to be sure. So this symbol is for the normal resistor. This symbol is for the variable resistor. This symbol is for thermistor. This symbol is for the LDR, that means like light coming there. And this symbol, as you're gonna see a lot later, it's for the diode. Okay? So this is the ending for the videos. Please, if you have any question, you can ask, and we'll continue later with 8.07. But now this we say 8.04 to 8.05 and 8.06 from page 178 until the page 183. That's all for this video. Thank you for listening. Take care of yourself. Don't forget to wear your mask and wash your hands. Stay safe.